This is probably the biggest day for this university since Stephen King matriculated in 1965. You all, we are present at the unveiling and development and initiation of world-changing technology. I mean, I'm not kidding. Can you imagine being able to tell your grandchildren, I was there when they invented the hammer? This is in that same category. This is going to change everything. 3D printing is a revolution in manufacturing in every way. In the military, for example, one of our problems is spare parts. We have a problem with aircraft that are these incredibly complicated, expensive aircraft that can't fly because they lack a part. In the future, there's going to be a little 3D, perhaps not this size, but a 3D printer in every hangar of the Air Force, and if they need a part, they can print it that day.
On your mark, go. It's unveiled 3 years ago. Congratulations.
So the print volume is 60 feet long by 22 feet wide by 10 feet tall. The extruder is currently set up to feed about 120 pounds of material per hour, but the machine is capable of feeding up to 500 pounds per hour with a bigger extruder. Right now it's set up with a 0.4 inch or 10 millimeter nozzle, and the bead size that it prints out is half an inch or 12.5 millimeters by 0.2 inches thick, so 5 millimeters thick.
Wow. Okay, and the materials that you're using right now?
Right now we've been using PLA, Woodfield PLA, which is the material we've developed here, and carbon ABS, because that's been commonly used in the large scale printing, but we could print almost any thermoplastic on the machine. Well, I come from a boat building background, and boats seem like an obvious choice for large scale printing. A lot of boats are already plastic. I mean, cars typically aren't plastic. Airplanes are a bit too high-tech and highly loaded, but boats make a lot of sense. They're large, they're complex shape, but they're not hugely highly loaded unless they're very fast boats. So they're already made of wood or composites. So it seemed an obvious choice to me as an engineer who's designed a lot of boats that boats should be printable.
So let's talk about the bolt print. So how long did that take, and anything we learned from printing that we might do differently, or?
Sure, we took the boat was an existing design from a client of ours called Navitec, who designs high-tech boats. So they had a design, we had to tweak it a little bit to make it printable. We printed it using a 45-degree printing technique that we've developed here on large-scale printers. The print took 70 hours to print, used about 5,000 pounds of carbon ABS, and we learned that it went pretty well. There's some things we do a bit differently. The controlling layer time is quite important, so the slicer can't actually control that very well, but layer time is very critical for large-scale printing to get good bead adhesion. You want it not too hot and not too cold, so you want to control the layer time within a certain tolerance. So having that automatically calculated by the slicer would be great. Right now it's not, it's kind of done manually. You sort of tweak it as you go through the print, which isn't ideal.
So on a printer of this size, we're not worried about part cooling fans, we're worried about trying to maintain the heat.
Yeah, the bead holds, because the bead's so big, it holds the heat, and you want it to for a certain amount of time, because you're also printing large items, so it takes a while to get all the way back around to where you started again. In the future we might put some cooling on there so we can print faster and faster. Right now we typically work with between a 1.5 minute and a 4 minute layer time with carbon ABS. It's different for different materials.
So we've got the boat, we've got and you also did a shelter, and talk about that a little bit.
We do a lot of work with the Army in a particular branch down in Massachusetts that deals with shelters. So I can't talk too much about that work, but they asked us to print a demonstration shelter. This was the sort of shelter that goes, it's a little command post that goes on the back of an army truck. That was about a 2,000 pound print. It took about 40 hours to print. Now interestingly, large 3D printing has different opportunities and different weaknesses compared to small 3D printing. So bridging is not an option. The bead's so big, so heavy, and holds so much heat, it just sags. On small printing, you can bridge 5 inches if you really want to, if your cooling's dead on. Small printing, you can't really, on the small scale printing, you can bridge a long way. On the large scale printing, you can't really bridge more than an inch or so, because it just the bead's got so much weight to it and so much thermal mass that it doesn't cool down quick enough. So infill isn't really an option. So a lot of these things we're doing now, I mean, infill has been used a bit, but a lot of what we're doing now is sort of perimeters. So the boat, we're just printing the shell and a couple of internal ribs, which are hard to model with the size of technology we have now, and that complicates things. So we also, you know, the 45-degree overhang is pretty strict. You can really push that quite a lot further on the small printers, again, because of the cooling. But on the large printing, that's tough, because the bead has so much mass. We haven't had the printer very long. We may be able to push the envelope a little bit, but